There's a color on a weather map that forecasters use so rarely, entire years sometimes pass without it ever appearing. It is called high risk, level 5 out of 5 on the Storm Prediction Center's severe weather scale, and it is marked in deep magenta purple. When that color shows up, it means meteorologists believe a major, potentially historic tornado outbreak is about to unfold, and it almost always shows up right as a stubborn heat dome finally breaks apart. This is not a rare coincidence. It is a documented, repeating pattern, and understanding it explains exactly why the days right after brutal, record-breaking heat are often the most violent days of the entire severe weather season, sometimes producing more tornadoes, more structural damage, and more loss of life than the heat wave itself ever did. Let's break down exactly how the Storm Prediction Center's color-coded risk system works, why heat dome collapse so reliably produces the rare magenta category, and what recent real-world examples reveal about just how dangerous this transition can become. Here is how the severe weather outlook system actually functions. The Storm Prediction Center issues a daily outlook using 5 escalating risk categories, each representing the likelihood and intensity of severe thunderstorms forming somewhere. Within 25 miles of a given point, marginal risk, the lowest tier, is shaded dark green. Slight risk moves up to yellow. Enhanced risk becomes orange. Moderate risk turns red. And high risk, the rarest and most extreme category the agency ever issues, is marked in that distinctive magenta purple. Forecasters reserve high risk almost exclusively for major tornado outbreaks involving numerous strong to violent tornadoes, and occasionally for derechos capable of producing widespread destructive wind gusts across an enormous area. These outlooks are typically issued only on the actual day of the event, because the atmospheric ingredients required to justify that top-tier designation are so extreme that forecasters need near certainty before using it. Just how rare is this designation? Looking back across the historical record, high-risk days occurred far more frequently in past decades than they do today, with 34 issued during the 1980s alone and 60 during the 1990s. That frequency has dropped substantially in recent years, with entire calendar years including 2015, 2016, 2018, 2020, and 2022, passing without a single high-risk day being issued anywhere in the country. When one does finally appear, it tends to draw immediate, serious attention from meteorologists, emergency managers, and the public alike, precisely because its rarity signals just how extreme and well-supported the underlying atmospheric setup has to be before forecasters are willing to commit to that top-tier warning. Here's the direct connection to collapsing heat domes. A heat dome represents days, sometimes weeks, of trapped atmospheric energy and moisture accumulating beneath a stubborn ridge of high pressure. When that ridge finally breaks down, usually because a strong disturbance or a deep digging trough finally manages to displace it, all of that stored up instability does not dissipate quietly. It gets released explosively, often producing exactly the kind of extreme, rapidly organizing severe weather setup capable of justifying a moderate or, in the most extreme cases, a high-risk designation. Recent real-world examples make this connection unmistakable. In March of 2025, a Storm Prediction Center high risk was issued for parts of Mississippi and Alabama, an outbreak that ultimately produced 41 tornadoes, including a violent EF4 and 11 fatalities. Just weeks later, in early April of 2025, another high risk was issued across Arkansas, Mississippi, Tennessee, Missouri, Illinois, and Kentucky, part of a broader multi-day tornado outbreak and flooding event that produced 93 tornadoes, and tragically, 24 total fatalities across its full multi-day span, with damages reaching roughly $4.1 billion. Both of these events developed as a powerful ridge of warm, unstable air collided with an approaching cold, energetic trough, precisely the atmospheric signature of a heat pattern finally breaking down under pressure from an advancing storm system. In both cases, the region affected had spent the preceding days under unusually warm, humid conditions, the kind of setup that builds exactly the atmospheric fuel needed for the violent transition that followed. If this breakdown is helping you understand exactly why these storm maps turn such an alarming color, do me a favor and tap that like button. It genuinely helps this channel keep making videos like this one. This same pattern showed up again in 2026. In April, a major tornado outbreak swept through the midwestern United States, the upper Midwest, and the southern plains, producing 86 confirmed tornadoes, including a powerful EF3 that struck Ringgold, Wisconsin, with winds reaching 145 miles per hour. The Storm Prediction Center escalated its outlook to a level 4 moderate risk, shaded in that urgent red color, one step below the rarest magenta tier for parts of Oklahoma, Kansas, and Missouri, while a hatched elevated tornado risk zone covered southwestern Wisconsin and neighboring parts of Iowa and Minnesota. That outbreak developed directly along the boundary of a retreating warm air mass, finally giving way to an advancing cold front, the exact same mechanism responsible for the deadlier magenta-level events the year before. It helps to understand exactly why this transition zone produces such extreme severe weather, rather than the heat itself simply fading away quietly. A heat dome creates a sharp, dramatic temperature and moisture contrast at its edges, warm, humid air trapped underneath the ridge butting up directly against cooler, drier air pushing in from an approaching system. That sharp boundary, combined with strong winds aloft, typically accompanying the trough responsible for finally breaking the ridge down, creates exactly the kind of wind shear and instability combination capable of spinning up powerful, long-lived supercell thunderstorms, the storm type responsible for nearly all of the most violent tornadoes ever recorded. There is a specific meteorological term worth understanding here, since it appears constantly in forecast discussions surrounding these events. Meteorologists refer to the boundary between the trapped warm sector and the advancing cooler air as a dry line or cold front, depending on the specific moisture characteristics involved, and the atmosphere directly along and just ahead of that boundary is where the most extreme instability tends to concentrate. Forecasters specifically watch a measurement called CAPE, or convective available potential energy, which quantifies how much fuel is available for a thunderstorm's updraft. During a heat dome's collapse, CAPE values can spike dramatically as the warm, humid air trapped for days finally gets forced to rise rapidly along the approaching boundary, sometimes reaching levels several times higher than what a typical garden-variety thunderstorm environment would produce. This is precisely why meteorologists watch the days surrounding a major heat dome's collapse with such heightened concern, often well before the actual severe weather outlook reaches its highest tiers. The heat itself, however dangerous and headline-grabbing on its own, frequently turns out to be only the first half of the story. The second half, the violent transition as that trapped energy finally gets released, is what produces some of the most destructive, sometimes deadliest tornado outbreaks of the entire year. There is also a timing element worth understanding, because it explains why these events can catch communities off guard even when forecasters see them coming days in advance. A heat dome can sit in place for a week or more, lulling the public into a sense that the biggest danger is simply enduring the heat itself, checking on elderly neighbors, staying hydrated, and waiting for cooler temperatures to finally arrive. Then, sometimes within a span of just 24 to 48 hours, the entire pattern flips, and the same region that spent a week worrying primarily about heat exhaustion suddenly finds itself under a moderate or high-risk tornado outlook instead. That whiplash, from a slow-moving, gradually building heat hazard to a fast-developing, acutely dangerous, severe weather threat, is exactly the kind of transition that catches communities least prepared, precisely because the nature of the danger changes so quickly. So what should you actually do the next time you see a stubborn heat dome finally starting to break down in the forecast? First, understand that the transition period deserves just as much attention, if not more, than the heat wave that preceded it, since some of the most extreme tornado outbreaks in recent memory have developed during exactly this kind of collapse. Second, if you live anywhere within the broader region affected by a major heat dome, keep monitoring official severe weather outlooks specifically. Separate from simply checking whether temperatures are finally starting to drop, since a cooling trend on a temperature map can arrive at the exact same time a moderate or high-risk designation appears on the severe weather map. Third, take any escalation to moderate or high risk with genuine seriousness, since those top two tiers, while rare, have consistently produced a disproportionate share of the most violent tornadoes, largest hail, and most destructive straight-line wind events recorded across the country in recent years. It is also worth having a specific plan in place before that transition day actually arrives, rather than trying to figure out shelter options in the middle of an active tornado warning. Identify the lowest floor, most interior room of your home in advance, ideally a bathroom, closet, or hallway without windows, and make sure everyone in your household knows where that space is located and how to get there quickly. Keep a reliable way to receive warnings that does not depend solely on your phone, such as a battery-powered NOAA weather radio, since these transition day outbreaks can develop and intensify rapidly enough that relying on a single notification method carries real risk if that method happens to fail or go unnoticed at the critical moment. Emergency management officials also emphasize paying close attention to the specific language used in forecast discussions during these transition periods. Phrases like discrete supercells, favorable wind shear, or a well-defined dryline boundary are technical signals that meteorologists are watching for exactly the kind of organized, long-lived storm structure capable of producing the most dangerous tornadoes. When that kind of language starts appearing in your local forecast, alongside a heat dome that has been sitting in place for days, it is a strong signal that the transition itself deserves your full attention. not just relief that the extreme heat is finally coming to an end. The bigger lesson here is that a heat dome rarely just fades away peacefully. It builds up energy, sometimes for weeks, and when that energy finally gets released, it tends to get released all at once, often producing exactly the kind of extreme severe weather setup capable of turning a forecaster's map that rare, unmistakable shade of deep magenta purple. Understanding that connection, rather than assuming the danger is past once the extreme heat itself finally starts to break, is exactly the kind of awareness that can make a genuine difference when the next major heat dome across the country finally begins to collapse. That awareness matters even more given how consistently this exact pattern has repeated itself across recent years, from the deadly March and April outbreaks of 2025 to the widespread, damaging tornado event that struck the Midwest and upper Midwest in April of 2026. Each of these events followed the same underlying script, a period of sustained heat and humidity building beneath a stubborn ridge, followed by a sudden, often violent transition as that trapped energy finally collided with an advancing disturbance, recognizing that script in advance rather than only after the map has already turned. That rare, alarming shade of purple is exactly the kind of preparation that genuinely saves lives. Weather maps are built to communicate urgency at a glance, and the rare appearance of magenta on an otherwise familiar green, yellow, orange, and red scale is designed to do exactly that, cut through the noise and tell you, in a single color, that this is not an ordinary severe weather day. If this video helped you understand exactly why this heat dome's collapse turned storm maps deep purple overnight, make sure you are subscribed, because there's a lot more of this kind of breakdown coming, and you will not want to miss it.